Okay, good afternoon, everyone. I'm going to start with just a few minutes to discuss the project before we get started with lecture today. So you should all have taken a look at the project by now. Hopefully picked out one that you are interested in doing, whether it be one of the ones suggested in the handout or anything else that you would like. And have thought about an introduction. It can be rough at this point. This is the first time that many of you are doing this, and that's just fine. Sorry, I'm getting you started on it early. So you've been randomly assigned to a group, and you should be able to find that. And there is a discussion board for your group, which has 4 or 5 students in it, which is a place for you to post the bits of your project as they come along and see what the other people in your group are doing. And you can also ask questions of Tony and me, and we'll take a look now and then at these forums. And we will use these forums as the primary basis of your participation grades in the course. So do post your things there and provide feedback on the things posted by your colleagues. So the introduction section is usually just 1 page of your poster. It's not too much, and it is usually bullet point. As most things on the poster, you don't want to have too much text there. It can be paragraph format, but there's a temptation in paragraph format to put too many words for a poster because people are only going to look at your entire poster, which is going to be like 9 or 10 sheets for like a few minutes, no more than 5 minutes. So it needs to just have a bare minimum of concise information on it. So your introduction, the ideal introduction, I think, will have a series of maybe 5 to 8 bullet points, something like that. In each one, you will have a piece of information like one about what the data set is that you're using and how it was collected, one on what your study objective is, and something about how you try to accomplish those objectives in this study. So it's just a very quick way for someone to look and know immediately what your project is. Like, you know, what are you doing? If someone asks you in an elevator and you have like 5 floors without stops to explain to someone what your project is, that's your introduction on a poster. It's just very quickly, you know, what is your purpose? What is your data set? What do you do? And you don't even have to say in there anything about your results or your findings. It's just background for your study. So it shouldn't take you too long to do for this purpose. It's not a whole lot of text, and it's just the background. Yes.
We're deciding as a group which topic.
No, individually. There's no need for everyone in your group to do the same thing. These are individual assignments. It's just peer review.
Okay.
But yeah, I expect people in the same group to be doing different projects. That's fine. Yeah, everything here is it's all individual assignments. The purpose of the groups is just to provide to let you see what some of the other people in your class are doing and to provide feedback, without it being like the overwhelming everyone posting their things, in which case you're less likely to look at everyone's things, and there will then be some people who nobody provides feedback for. This is just a way to ensure that everyone's bits get looked at and get feedback on.
Are you and Professor DeVito going to provide direct feedback to us about the proposed intro? Like, if you think it's not a good project, you know, you can let us know.
I wonder, is there a method of like tagging people in the things. The problem that I have with Blackboard discussion boards is that I don't get any notification if there's like a question for me or something, because I'm more than happy to go in and answer some questions, and that I generally can't keep up with all of the discussion that is going on there. But I will probably take a look once a week and see what people have posted there. But I don't want to replace the peer review process. Like, you know, I can provide some overall ideas of about what you're doing, but I'm not grading these intermediate pieces.
Can we email you with our like proposal? Yeah. What do you think?
Maybe what you can do is let me know that if there's a question for me in your group, let me know which group it is, and then I'll go take a look. I'll go take a look there. Any other questions about the assignment? Seem clear so far? Okay. Great. So with that, let's get started. I'm going to start out with, I know we didn't finish with the analysis of variance last class, but I want to make sure to properly get through the chi-squared and analysis of categorical variables today. So I'm going to do that first, and if there's time, I'll finish what I didn't do from last lecture. And if there isn't time, I'll just put a recording to the rest of the lecture from last time, because you're definitely, or most people are going to use chi-squared tests in their projects. You may or may not use analysis of variance. So, so I want to make sure to get through chi-squared analysis today. All right, so we're going to start analyzing categorical variables today. We've done a whole lot of stuff with the normal distribution, the t-distribution, all this stuff for continuous variables, and we haven't done anything for categorical variables, especially because we didn't really cover analysis of variance last class. But today's class is all about describing and hypothesis testing for two categorical variables. And we'll do this with Pearson's chi-square test and write out our so-called R by C tables, rows by columns tables, define relative risk and odds ratios, and I'll just introduce to you some alternatives to the chi-square test. And all this is in your book chapter 6. I found an interesting data set as a motivating example for this, and there is a paper that analyzed this data set in posted on Blackboard with today's lecture, and it was a study of all court trials concerning homicides in Florida over about a 10-year period, where they analyzed the for each of these were convictions, and they analyzed whether the death penalty was given to these convicted murderers according to race of defendant and the race of the victim. So first, we have this table that is the death penalty verdict, whether death penalty was given to this defendant according to the race of the defendant. So this is a 2x2 contingency table with the margins filled in here with the total. So it's a total of just over 10,000 defendants, almost evenly white and black. And a large majority of them were not given the death penalty, only somewhere around 4% or 3.5% of them were given the death penalty. So So the first question that they asked here was, does there exist evidence of discrimination in the death penalty verdict? And put otherwise probabilistically, is death penalty verdict independent of the race of the defendant? So, how are we going to do this? We need to write down a null hypothesis, and as usual, that null hypothesis will be a hypothesis of no association. In other words, that the race of the defendant is independent, not associated with death penalty verdict. So writing out using our H0, death penalty verdict and race of defendant are independent, and the alternative hypothesis is that they are not dependent. Or equivalently, the probability of death penalty for white defendants is the same as the probability of death penalty for black defendants, as the null hypothesis, with the alternative hypothesis of them being not equal. We could do this either using a proportions approach, using the normal approximations, and perform a two-sample z-test, or construct a confidence interval using methods that you've learned already. This is a large sample. There are definitely no cells in that contingency table with an expected number of verdicts less than 5. So this would work pretty well. Or you can use the contingency table approach, which is to compare the counts that we see in the table to what we would expect under the null hypothesis of no association. And if the observed counts differ greatly from what we expect when there's no hypothesis, then we become more likely to reject the null hypothesis. So what do we expect? And we can actually fill in this table again from the margins based on a null hypothesis of independence. So how do we do that? Well, let's start with one table here, the top left table for white defendants who received the death penalty. So the probability of being in this cell is just under independence. Remember that the probability of two events is just the product of them independently. That is under if these two events are independent, so it's just the probability of the defendant being white times the probability of them receiving the death penalty. And that is something easy to calculate here because the probability of being white in this study is 4909 over 10,068. It's just under 50%, and the probability of receiving the death penalty is 364 over 10,068. So it's just 4909 times 364 over 10,068, which gives us, so if this were divided by 10,068, that would give us a probability, but if it's as written here, it gives us a number, 177.5. Right, so these two probabilities, there would be 10,068 twice on the denominator, but for a count, there's just this number once on the denominator. Any questions about this so far? Do you think if I gave you a table like this, you could fill in this number? Yeah, you just take these two margins, multiply them, and then divide by the total number. I feel like there's still a little bit of puzzlement.
Why are we calculating with the 364 instead of actual number of white with the verdict yes?
Instead, well, because this is what we would expect if there is no dependence. So here, there might be dependence. This is the actual data we observed. Here, we're going to fill this in again with what we would expect if there's no dependence. So that's why we're not using the actual number from here. We're filling in instead what it would be if there's no dependence. Right, Tony?
Correct. But it crowd things out after the exams, right?
Yeah. Okay, so we've got one cell filled in here. Now for the other ones, we could go about it exactly the same way. For this one, we could go 4909 times 9704 divided by 10,068. Or what's another way you could fill in this cell?
Minus.
Yeah, just 4909 minus this. So you only have to do that probability calculation once because you know that the rows have to add up to these marginal values, the columns have to add up to these marginal values. So you don't have to do that calculation for every one. And in fact, the number that you have to do that calculation for is your degrees of freedom for an R by C table. So for a 2 by 2 table, it is 1 degree of freedom because you only have to fill in one of those squares and then all the rest are fixed.
What does R by C stand for?
Rows by columns.
2 by 2 tables.
Yeah. Yeah. So, but it could be a 2 by 3 table, in which case you need 2 of them to fill in the rest. There's 2 degrees of freedom. In a 3 by 3 table, you need 4 of them. See if I can draw that out. So 3 by 3 would look like let's see. So this one, just having 1 filled in is not enough because you don't know what's in these 2. But if you had these 2 filled out, then you could complete that. And if you had this one filled out, then you could complete here. If you have this one filled out, then you can complete this bottom one, you can complete this one, and you can complete this one just by doing that subtraction from the marginal totals. So in a 3 by 3, there are 4 degrees of freedom. So going ahead and doing that for this table, we can fill in the entire 2 by 2 table with what we expect under the null hypothesis of no dependence between verdict and race. And this is based on that probability rule that you learned several classes ago that for independent events, their joint probability is just equal to the product of the 2 independent probabilities. Having calculated this table, you can now calculate your Pearson chi-squared statistic. And it's simple. All it is you go over the table, and for every cell, you take what you observe in that corner minus what you expected, square it, and divide by what you expected. Sum that over the whole table, and that is your chi-squared statistic. With one little exception that in 2 by 2 tables, we often use so-called Yates correction that is a bit more accurate for the 2 by 2 table. You just subtract 0.5 from each of the cells. And under this null hypothesis of independence, chi-squared follows a known distribution, the chi-squared distribution. And there's a different chi-squared distribution for every number of degrees of freedom. So it's like the t-distribution that way, in that there's a different distribution for each degrees of freedom. But otherwise, this is now going to work basically like the other hypothesis tests that you've learned, like your z-test, like your t-test. It's just a matter of comparing your test statistic to the test statistic under the null hypothesis. And if your test statistic lies far enough out into the tail, that so-called rejection region, then you reject your null hypothesis. And that's all there is to it. With one exception, that it's actually simpler in that we only ever use the right tail for the chi-squared test.
Why?
Well, good question. Why? And I think I get to that in a bit, but I'll tell you now. So here's what a chi-squared distribution looks like. This is the table from the appendix of your textbook with. It looks a bit like your t-test table in that there are all these different degrees of freedom, and there are your rejection regions for each of these different alphas. This is what the chi-square distribution looks like. It's right skewed, and it has a long right tail. Who wants to take a guess at why we only reject if it's under this tail? And not if it's like under this tail. Let's look at the definition of this again. So if we have actual dependence between our variables, what happens to chi-squared? When the observed values become more and more different from the expected values, what happens to chi-squared?
Bigger.
It gets bigger. Yeah, it doesn't matter in what direction, whether in a particular cell the observed value is bigger or smaller than expected because it's squared, whether it's bigger or smaller, chi-squared always gets bigger. If there's dependence between these variables, chi-squared gets bigger. Can you imagine any situation where you would get a value way down in this tail? So that means that your observed values are actually very, very similar to the expected values. Suppose that all of your observed values are exactly the same as your expected values. How could that happen? Seems pretty unlikely, doesn't it? It means like, you have the hypothesis, you think that there's no relationship between race of the dependent and application of the death penalty, and lo and behold, you see exactly what you expected under that null hypothesis, no deviation from it. Doesn't sound very likely, does it? No, and in fact, there have been at least one instance of data analysis, fraudulent data analysis uncovered that way by observed values that match too closely to the expected values. In fact, much more closely than you expect under the null hypothesis, to the point that the only reasonable explanation for it was data manipulation. Because this chi-square distribution tells you that if there is exactly no dependence between these two variables, this is the distribution. This is the distribution of chi-squared values that you expect. So if you get a value where there is, less than a 0.001 probability of getting something that small, there's no good explanation for that, other than extreme chance or some kind of manipulation.
We're working, you said the 2x2 table is always 1 degree of freedom.
Yeah.
So in what instance would we be looking at a row in that table that is more than 1 degree of freedom? I feel like we would work with a lot of crosstabs.
Well, if you, instead of just black and white race, you had black, white, American Indian, then you would have a 3x2 table. Or if you added, instead of just death penalty or not, you added mistrial. So, you know, there's more than 2 options, more than 2 categories in your variable.
Is there a formula to figure out how many degrees of freedom there are based on the dimensions of a table?
Good question.
Can we say it's rows -1 times columns -1?
Rows -1 times columns -1. That sounds right.
Which on one of the,
I would have to test it though.
on one of the previous slides, I think you had.
Let's see.
Yeah.
R -1 by C -1 degrees of freedom. Right, you are. The number of rows -1 times the number of columns -1.
So in a 2x2 table, there would be 1 degree of freedom.
Right. In a 2x2 table, there's 1 degree of freedom.
Same way in 3 column, that would be 4 degrees of freedom, right? 2 2s are 4.
With a 3x3, it would be 4
Yes.
degrees of freedom. That's right. And we're never going to analyze in this way a 1 by something or a something by 1, because then dependence doesn't mean anything if one of the variables only ever has 1 value. So it's not, there's no chi-square distribution in that instance. All right, so we've discussed most of these things now, but to review, if the columns are independent, then these observed and expected values shouldn't be too different, and the chi-squared value will be small, but not too small. Whereas if there is dependence, then the observed values become more different from the expected values, and we get a large chi-squared value. And if chi-squared is large enough that it lies up in the rejection region of our chi-square distribution, which comes from the null hypothesis, then we'll reject the null hypothesis and say that the variables are independent. So this alternative, it's an inherently two-sided or multi-sided alternative in that it doesn't matter what the direction of the association is, but we don't double the right tail because we only ever look at one tail of the chi-square distribution. And just to make that explicit here, I don't know if you can see, if we were looking at an alpha of 0.05 and a 2x2 table, then our critical value of chi-squared is 3.841. So that's a pretty common chi-squared value to be used. So there are fewer assumptions than we are used to, but there are still assumptions behind this Pearson chi-square test. As always, we assume that these observations are independent, and you'll keep on making that assumption until you get into some things like hierarchical data analysis in your 3rd FE and BIOS classes. We assume that, of course, that the sample is representative of the population. We have to make that assumption. And we're also making a large sample size assumption here that, that similarly to when you were doing the proportions test, we're still, the chi-square distribution is correct under the null hypothesis. Approximately when no cell in the table is expected to have fewer than 1 count, and no more than 1/5 of them have fewer than 5 counts. So this is not a terribly restrictive assumption. And some software like R, I know, although I don't know about SPSS, have an option to to actually do a permutation test if you have a smaller sample size than this. So it gives you a still inaccurate p-value for small sample sizes. For small samples, the alternative is the exact binomial test. As I'll mention later, there's another test called Fish's exact test that people often use as the alternative, but it's not really an alternative to the chi-squared test, and it's, I think, a bit of a misnomer that it is frequently treated as such. I'll talk about that later, though. But there are no assumptions required about the population distribution. It's just a categorical variable. There isn't such a thing as a distribution as in with the normally distributed assumptions that we've made before. So let's go ahead and do it for this example. We've got our observed counts, the expected counts here, and this gives us a chi-squared statistic of 39, which is way larger than that 3.8 or something. And it corresponds to a p-value of something very, very tiny. So clearly these variables are related. There is a relationship between defendant's race and the death penalty. So we reject that null hypothesis of independence, and then we ask, okay, where is that association coming from? Well, the proportion of death penalty verdicts among white defendants is about 5%, and among black defendants, it is only 2.5%. So it's actually lower for the black defendants. Of course, you'll have driven into your heads through all of your classes that correlation doesn't equal causation. This is an association, but there might be other factors involved here. But before we get to that, I'm going to introduce relative risk and odds ratios to you. So relative risk is a fairly intuitive measure, and it is just the ratio of probabilities. So using the terminology of conditional probability, it's the probability, in this case, probability of death penalty, conditional on the defendant's race being white, divided by the probability of death penalty conditional on the defendant's race being black, which is 1.94. So this is saying that if you are white, you have a 1.94 times higher risk of being given the death penalty. So that's a risk ratio. Odds and odds ratios are a little bit different, and they're less intuitive, I would say. Whereas risk ratio is just about probability. Odds is a probability divided by 1 minus the probability. So if you roll a dice and you want to know that your probability of getting a 1 is 1 out of 6, but your odds of getting a 1 are 1 to 5. So for high probability events like rolling a dice and like this, there can be some difference between risk ratio and odds ratio. And here so dividing by, so these are fairly low probability events, 5%. So this correction is fairly small. Dividing by 0.05, subtract this 0.05 from the denominator and 0.025. So the difference is not huge here. The odds ratio is 1.98 versus a risk ratio of 1.94. If these were higher probability events, there would be a larger difference between the risk ratio and the odds ratio. And generally, odds ratios are larger. There are two ways to calculate the odds ratio, looking at it as conditional probabilities. You can do it using this probability, so going back to a disease example, probability of disease given exposure. In this case, it would be probability of death penalty verdict given race. Or you can do it the other way, probability of race given death penalty, or probability of exposed being disease. Whereas with risk ratio, there's only one way to calculate it. Probability of disease given exposed, or probability of death penalty verdict given given race. So in this case, we could calculate both of them because we have both of these probabilities for our data set. But that's not always the case. So in a cohort study where we assume that our prevalence within that cohort are representative of the population, if it is a representative cohort, then we can calculate both things because we know the population prevalence. So you can calculate your odds ratio either way, and you can calculate your risk ratio. But in a case control study, you are explicitly picking out a certain number of cases, a certain number of controls. So that's not what we're talking about here. This was all of the death penalty cases in Florida over a period of time. It's not a case control study, it's a cohort study. In a case control study, it would be more like we take 50 death penalty verdicts and 50 that did not result in the death penalty, and then look at the race of those defendants. So that 50-50 probability has nothing to do with the prevalence of the death penalty in the population. And in this case, you can calculate the odds ratio, but you cannot calculate the risk ratio unless you know the prevalence of the disease or the death penalty in the population. So this is one reason to use odds ratio. Another one is that it turns out to be more convenient for logistic regression, for mathematical and statistical reasons, and also in your software. It is what you will, what your software will return to you. You will have to use Bayes' rule to calculate risk ratio from your odds ratio if you want to make that conversion, and you'll have to know the prevalence. And as I mentioned, for rare events, they're almost the same thing. So, you know, if you're talking about 1 in a million, then your risk and your odds are basically the same thing. But if it's something more common, like rolling a 1 on a die, then there's more of a difference between them. So I mentioned that maybe there is more to it than just that white defendants are more likely to be given the death penalty. And in this paper, they also looked at the distribution of death penalty verdict by the victim's race. So this should say victim's race, not defendant's race, because this is different. This is by the victim's race. Also, a large chi-squared statistic, and a very large odds ratio, in that if the defendant is white, the odds of receiving a death penalty verdict are much smaller than if the defendant is black. So it is also related to the race of the defendant. Just a sec, did I do this right here? Sorry, so this is for white victims only. So in this case, sorry, this is looking at the defendant's race stratified by race of the victim. So looking at only white victims, it turns out that in fact, whites have a much smaller chance of being given the death penalty. And then looking at only black victims, it turns out that whites have a much larger probability of being given the death penalty. So there's some kind of an interaction occurring here. And pulling this out from this nice summary table out from the original paper, in all cases there's a 3% chance, 3.6% chance for all defendants being given the death penalty. When you break it out by the defendant, it is higher for white defendants than for black defendants, but it is much higher for white victims. So the strongest difference here is if there's a white victim, there's a 6 times higher risk ratio of being given the death penalty. And then broken down by black kills white, white kills white by both the race of the defendant and the victim. By far the highest probability of receiving the death penalty is for a black suspect and a white victim. So what we're seeing here overall is really an averaging out of a number of different situations, and you start to see a more fine-grained picture of what is going on when you break it down. And in fact, when there's a black victim and a black suspect, there's a fairly low, that's a very common murder and a very low rate of applying the death penalty, which explains a lot of potentially, still this is not a causal study, but potentially explains something more about why there's the overall lower rate of death penalty being given to black defendants. So just to summarize, this is an example of an interaction, that there is some association between the defendant's race and the victim's race, and the chi-squared test doesn't tell us anything about this. This is more, it's a matter of being aware of these interactions, and then it becomes almost more a sociological question as to why this is happening and what the causality is. Yeah.
So it doesn't inform us where the departures from independence are. So the magnitude of the chi-square value doesn't matter as long as it's above the critical value.
The magnitude, these magnitudes are important for interpretation.
Well, not those, the chi-square value. So like for, what was it, 60 for, one of these was really.
So here it's 17, here it's 67.
Yeah, so you wouldn't look at that 67 compared to the 17 and say, this is where the departure of independence is, if it's higher than the critical value?
No, I would, so I use this chi-squared statistic just to say that there is a statistically significant departure from independence here. What I would use this table here for then going and trying to interpret the results, because the magnitude of the departure is important. But looking at it in terms of risks and risk ratios is important.
Okay.
I mean, the magnitude, so if you were looking at a 3x3 table, the magnitude of chi-squared does tell you something about how big the departure from independence is. So this is a larger departure from independence than this one is. So if you don't, if it's a 3x3 situation or something where you can't use risk ratios or odds ratios, you could depend on the chi-squared, but in this case, really, the risk ratios are much more interpretable than chi-squared. So in this situation, my preference would be to use the chi-squared test just to reject the null hypothesis, and then use the risk ratios to discuss where those departures occur and how big they are. My preference is always to use some measure of the strength of association to report and discuss results, and just use the statistical test to reject the null hypothesis. So it allows you to discuss these magnitudes without reading tea leaves and reading into departures that can be explained by chance. You know that it's probably not explained by chance, but then you go into the numbers and just discuss the risks, the risk ratios. This is and that's actually an important question. The use, it probably goes under the use and abuse of statistical tests, and treating a very, very small p-value as something that is then very, very meaningful, I think, is an abuse of the hypothesis tests. But really the purpose of the hypothesis test is just to help you reject the null hypothesis. And then after you reject the null hypothesis, you really want to look at more interpretable things like risks, like correlations, like differences in means to actually interpret and discuss your results. So a couple related tests. McNemar's test is for paired samples. Your exact binomial test you can use for small samples. And this Fisher's exact test is a very popular one, and actually I have seen it used frequently for 2x2 tables when there's a small sample size. People will say, because the sample size is small, we use Fisher's exact test. But in fact, the null hypothesis is different for Fisher's exact test. And it's actually a really cool paper, this original paper. It's very interesting for a theoretical statistics paper. And R.A. Fisher discusses the situation which made him devise the test. And the situation was that a lady was given 10 cups of tea, where so the situation was this lady claimed that she could tell whether the milk had been added to the cup before the tea, or whether the tea was put in and then the milk, and then it was stirred. And it made a difference for how the tea tasted. And Fisher didn't believe it, and so he designed an experiment to test this hypothesis that the lady could tell whether the milk was added first or the tea. And the experiment was that you give this lady 10 cups of tea, 5 of them where the milk was added first and 5 where the milk was added after the tea. And then in the hypothetical experiment in the paper, she correctly identifies all 10. And Fisher calculates what is the probability of this under the null hypothesis that she's simply guessing. But a key part of this guessing is that she is told that there will be 10 cups of tea and 5 of them will have the milk added first. So she knows that she should guess 5 and 5. And another way of saying that is that the marginal totals of this table are fixed by design. So the marginal totals are that there are 5 with the milk added before, 5 with the milk added after, and her guesses will be also 5 and 5. Or her guesses could be different, but they're fixed by the design of the experiment. So in many cases, like the death penalty verdict, when the marginal totals are not fixed by design. So Fisher's exact test is the wrong hypothesis test to use. So it gives you an exact p-value for a different null hypothesis. And it really should not be treated as an alternative to the chi-square test. And I think you'll be a step ahead of a lot of people doing public health data analysis if you remember that. In practice, often the p-values are not that different, but there are some cases where the p-values can be quite different. So to wrap up, we're talking today about methods for hypothesis testing on two categorical variables with a null hypothesis of independence between those variables. In this case, the tests are inherently two-sided in that it doesn't matter what the direction of the dependence between them is, but still we only use the right tail of the chi-square distribution. We still have type 1 and type 2 errors, just as we did before. So let's take, trying to think, we have time to do a little bit of analysis of variance here. We don't have much. Is there some interest just to quickly go review the analysis of variance right now as opposed to, okay, let's do that. Analysis of variance is important. Let me see. I think we made it to about this far. Let's see, actually I'll go up to this spot. So this was an example where there were three different training methods for something, and we have samples of learning times for different individuals for each of them. And making a box plot, you see something that looks like we have two training methods that are about the same, and a third one that is different. And analysis of variance is a hypothesis test where the null hypothesis is that the means are the same in all of these categories. So that the categories do no more to explain differences in means than they would if the observations were assigned to random categories. Let's see, is there? We actually have the full data set here. There's only 3 observations for each of the methods. So you can see that these observations are pretty similar for method 1 and kind of different for method 2. And the question is this a difference that's due to chance, or is method 3 really something special that results in worse learning times than the other 2? So you could do this using 3 different t-tests, method 1 versus 2, 1 versus 3, and 2 versus 3. There are a couple of problems with this. The main one is that as we start doing more tests, this is called multiple hypothesis testing, and if we control the probability of type 1 error for one of these tests, we're no longer controlling it as we do more and more tests. Your probability of making at least one type 1 error increases as you do more and more tests. So what we're going to do instead is just a single test for whether there is a difference anywhere between these categories and control the type 1 error using an analysis of variance. So it's going to compare the difference in means between 2 or more populations without doing a bunch of pairwise tests. Noting that if we were to do these pairwise tests, the probability of making 1 or more type 1 error is actually almost tripled to about 14%, even if we're controlling it at 5% for each one of these tests. That's because the probability of not making an error for one of the tests is 0.95. If these are independent tests, then the probability of not doing it 3 times in a row is cubed, and the probability of having done it at least once is 1 minus that. So the more and more tests you do, the more and more that type 1 error gets inflated. It is essentially a comparison to the variance within these groups to the variance between the groups, in that if there is a lot of variation within the groups compared to between the groups, it's going to be hard to distinguish between the groups. Whereas even with the same group means, if the variation within the groups is small, it's easier to see a difference between the groups. So in this case, this looks less likely to occur by chance than the picture on the left. Let's skip over this. This is just a review of our terminology. That population means are mu, population standard deviations are sigma. I lost the x bars here, but the mean should be x1 bar, x2 bar. Let's see if I can. X1 bar, x2 bar. Dot, dot, dot. And standard deviations, as usual, are S's. So we have potentially different means and standard deviations for each of these groups. We're calling our null hypotheses when we were doing one sample ZNT tests. The null hypothesis was that the mean of that one population was equal to a hypothesized mean under the null distribution. For the 2 sample test, the null hypothesis was that the means of those 2 populations was the same, alternative that they're different. We now have multiple populations, and our null hypothesis is that all of those population means are the same for 3 or more groups. And the alternative hypothesis is that not all of them are identical. It doesn't say anything about which ones are different, just that they're not all identical. Does that make sense? So it's a little bit like the chi-squared test, in that if you reject the null, it tells you that there is a departure from independence somewhere in the table, but it doesn't say where. The analysis of variance tells you that there is a departure from equal means somewhere, but it doesn't say where.
What kind of test would that inform after? Like, where would you go from there to get like something that makes sense?
We'll get there. After you do this, it is appropriate to do pairwise comparisons. You can do pairwise comparisons, and there are multiple hypothesis corrections that you can do for those pairwise corrections after you've rejected the global null hypothesis with an analysis of variance. You can also just use a box plot and look and see where the differences seem to lie. There's differences in opinions about whether you should do more hypothesis tests or just look at a box plot and say where the biggest differences lie.
Speaking of box plots, I noticed on the assignment for project that there's an emphasis on including box plots on the poster? Is that?
Well, if it's appropriate. So for not all data, it's not appropriate for all data sets.
Okay.
For the project, really, the things you're actually graded on are presentation. Is the presentation clear and easy to follow? And are your analyses appropriate for the data and the objectives? And are your conclusions drawn correctly from your analyses? That's it. So, you know, you don't have to have box plots. But if it's a data set where box plots would be appropriate, then you should as part of your descriptive data analysis. Assumptions behind ANOVA are that the data are approximately normally distributed or that you have a large sample size. But you should note that that ANOVA is robust and conservative to violations of this assumption. There's some departure from normality. It takes a significant departure to impact your ANOVA results, especially if you have a sample size. If you have a sample size of something, this should be greater than 40. Or sorry, this is, yes, a sample size greater than 40, even with skewed data and outliers, analysis of variance is very robust. It becomes somewhat less so for smaller sample sizes. I should note there are tests of normality for data, but I remember in one textbook I read, it said doing a test of normality to decide whether it's appropriate to use an ANOVA is a little bit like sending a rowing skiff out on the ocean to see if it's calm enough for an ocean liner. In that those tests are very sensitive to departure from normality, and ANOVA is not. So you can tip over your rowing skiff with your test for normality when it would still be fine for an ANOVA. Also heard some statisticians refer to ANOVA as a non-parametric test because it is so robust. So it's a very useful test. We make the assumption of homoscedasticity, which is to say that the standard deviations are equal in those groups. But again, tests of equal standard deviation are not recommended as a prerequisite. But if there are observed standard deviations differing by more than a factor of 2, you may want to consider an alternative to analysis of variance. And as usual, randomization, that this is a representative random sample. And so if it is a survey that we have drawn these randomly from the population, if it's an experiment, that the subjects have been assigned randomly to your groups. I'm going to skip a bit over the calculation. And just tell you about the F statistic here, that it is a ratio of the between groups standard deviation to the within groups standard deviation. And if you look at an ANOVA table, you will see lines on it for the it will break, it's an analysis of variance. It tells you the analysis of variance of the means. So it will look at the means of your groups and calculate the variance, and it will look at the residuals and give you the variance of that. And your F statistic is just the ratio of that. So if there's a large variability of your group means and a small variability of the deviance within those groups, then you're going to have a large F statistic, and you're going to reject the null hypothesis. It's like chi-squared in that it is a one-tailed test. You only ever look under the right-hand tail. Doesn't matter what the departures are. If there's a departure, it makes your F statistic larger. But it's a little bit more complicated than the chi-squared test in that there are actually two different degrees of freedom. There's the numerator degrees of freedom, number of groups minus 1, and there are also the denominator degrees of freedom. This is the residual degrees of freedom, which is the total sample size minus the number of groups. So there's a different F distribution for every numerator and denominator in that calculation degrees of freedom. So can someone just describe to me in words what the F statistic is when it is so under the null hypothesis of equal group means, what is the F statistic? Of course, all of our test statistics are true under when the null hypothesis is true. One? No. If the null hypothesis is true, it tells you that so if there are equal means in every group, you're still going to you're going to get positive or negative, or you'll get ratios that might be more than 1 or less than 1, but they will have distributions that look like this. And if you have, so let's see, numerator degrees of freedom of 1, you'll tend to have, so this is a small number of groups, that's only two groups. You'll tend to have an F statistic less than 1 because you have more residuals in your denominator. And as you get larger numbers of groups, so going up to 101 groups with, on the extreme here, we have 100 degrees of freedom on the numerator and 100 on the denominator. This tells you that with repeated sampling, you're going to get this distribution of F statistics if all of the groups have the same mean.
This distribution is showing you that what you can expect to get if the null hypothesis is true.
Yep. All of the test statistics that you've learned are what you get under repeated random sampling if the null hypothesis is true.
Okay, and the way you translate the D1 equals 1, D2 equals 1, that's degrees of freedom for the numerator and degree of freedom for the denominator.
Yep. So this would be, one numerator degrees of freedom would mean that there are two groups. One denominator degree of freedom would mean a sample size of 2 in that case. So it's a very small study.
So it doesn't matter how great the difference between degrees of freedom are. That's what it's designed. The F statistic is designed to correct for that.
Right.
What matters is.
What matters
is the actual ratio. Right.
What matters is the actual ratio compared to the distribution of ratios for those degrees of freedom.
Right. So it would be fair to say then, though, that the higher the ratio, or the greater the number of the bigger the F statistic, the less likely the null hypothesis is to be true.
Yep, that's right.
Okay.
Yep, as long as you're on the right-hand side of this peak.
Right.
Yeah, the bigger your F statistic, the less likely that is to occur by chance. And again, you don't really expect to be under the extreme left-hand side of this distribution. This means that your group means match really, really closely to your equal means. So under your null hypothesis of equal means, you would have, say, a mean of I don't know, what are our means here? So we have means of 12, 10, and 22. We would expect, so if all these were equal, I don't know, what's the mean of these three? 32, 44 divided by 3, that's about, 44 divided by 3, 14?
14.6.
14.6. So if we got exactly 14.6 in each of these, then that's probably actually closer than we expect those group means to be, even if in the population they're the same. You expect more random sampling variation than that. So that's, again, a bit suspect if you have two similar groups. All right, same story for the hypothesis testing. You get your critical value of F for your numbers of degrees of freedom, and then reject if your F statistic is within that rejection region. Same story. I think that I should probably wrap up here and let Tony take over with the lab. I think this is the main point. Actually, one more thing. So I'll just show you an ANOVA table. It tells you what the actual sum of squares, degrees of freedom, the mean. So the sum of squares for the between groups would just be the group means minus the overall mean, and those squared and summed up. And the mean squares is just that divided by your degrees of freedom. So there are three groups here, two numerator degrees of freedom. The group means minus the overall mean is 248. And on the denominator, these are for each data point, it's its value minus the mean for that group. And then those differences are summed and squared to give a total of 66 divided by the 6 denominator degrees of freedom here. And those add up to the total number of the total sum of squares, and the ratio of these two gives us the F statistic of 11.27. So you can do this hypothesis test yourself by looking at the critical value of F for 2 numerator and 6 denominator degrees of freedom, and then seeing that this ratio of 124/11, which is about 11, is something greater than the critical value of F at an alpha of 0.05 for 2 and 6 degrees of freedom. They're starting to all look the same, these hypothesis tests, right? Except for the degrees of freedom. So yeah, F statistic and p-value. So which brings us to your question about what do you do if you reject. One thing you can do is post hoc tests, which is comparing all of the pairs and the differences in those pairs. And there are procedures for doing this in every statistical package, including SPSS. And the common one you're probably going to use is the so-called Tucky method, which just does all pairwise comparisons. And if you choose the Tucky procedure after rejecting the F test, you will see a series of confidence intervals for each of the pairwise comparisons, with those confidence intervals corrected for multiple hypothesis testing. And it will tell you then which of those pairwise comparisons you can take as significantly different, the means are significantly different. There are a couple other methods. One worth mentioning is the Bonferroni method, which is strict and can be applied to any experimental design. And then there are a few other ones. Dunnett method for just comparing each of several treatments to a control, so not all pairwise methods, and the Sue method for just comparing the best of what you saw, so say the highest mean or the lowest mean compared to all of the others. So you can choose which contrasts you want to do. Confidence intervals if they are corrected, for example, with the Tucky method, you can use them in the way you're used to for doing hypothesis tests. And in your SPSS output, if you choose the Tucky method, you'll get an output table looking something like this with, so here method 1 compared to 2 and 3, method 2 compared to 1 and 2, and method 3 compared to 1 and 2. So it's actually giving you each result twice. Here's method 1 minus method 2, the mean difference is 2, and method 2 minus 1, the mean difference is -2. So there's some repetition in this table.
So how do you make sense of this table just in terms of like putting it in terms of like, so the significant, let's say from method 1 to method 2, so there's a 0.751 significance.
Yeah, so it's telling me that between method 1 and method 3, there's a significant difference, and between method 2 and method 3, there's a significant difference. And here, between method 3 compared to 1 and 2, this is just a repetition. These are the same rows again, just with the sign swapped.
And the confidence intervals are the confidence intervals that you calculate the same way as if you were just doing it.
These are corrected for multiple hypothesis testing, so it's not quite in the same way. They have an additional correction added. And I'm not getting into how that correction is done, but it's not just, if there were more tests here, these confidence intervals would get larger. And it is worth noting that you can have a significant F statistic and still see none of these differences get a significant p-value. It can happen because there's differences that overall reject the null hypothesis of all group means equal, but none of the individual differences are large enough to reject those null hypotheses for the individual pairwise comparisons. It's just graphical representation of the Tukey comparison. It looks like confidence intervals on the differences for each of these. So confidence intervals on the differences in means for each of the pairwise comparisons. So in this case, I'm just plotting what these lower bounds and upper bounds given here, and the confidence intervals do not cross 0 for the 2 versus 3 and the 1 versus 3, but they do, it does cross the 0 line for 1 versus 2. This got shifted over a little more, but this should be the 0 here. So just wrapping up now, null hypothesis for the F test is that there's no difference in the mean between 3 or more groups. So the response variable, the outcome variable is continuous, and our predictor variable or independent variable is categorical. It can be used also with 2 groups, in fact, and you will get equivalent results to a t-test. It's like the chi-squared statistic in that it's right skewed, and the rejection region is always on the right, and it has these same assumptions, including homoscedasticity. My terrible writing here, but yes, the assumption of homoscedasticity, independent samples, and normally distributed populations. And we follow up with the post hoc tests only if the F statistic is independent. Otherwise, you just reject, or you accept the global null hypothesis and don't do post hoc tests. And now we can wrap up and let Tony take over. Let's take a 5-minute break, and then we'll continue with the lab.